Yeah, Byron, and I'm going to talk about this idea of neural information retrieval. It's a sort of interesting new or emerging topic field and how we're applying it at Talla in a conversational question and answering agent. So just to give you a little overview of what we're doing at Talla, we're building this intelligent conversational service desk product, which is something that will sit between your employees and your internal service organizations like HR, IT, facilities, and able to help automate away some of the tedious, repetitive questions that they receive so they can focus more of their time on more complicated interactions and less time on answering simple questions that the employees would probably get if they just bothered to go, say, read their handbook. And so we've broken this up into about 3 different kind of pieces. There's this conversational knowledge base, which is the focus of what I'll be talking about a bit later. A basic lightweight ticketing system that we use as part of the human-in-the-loop-based approach to help train that knowledge base. And then this idea of intelligent workflows where you can do back and forth communication with people to gather feedback, to do polling, things like that. So I want to talk about chatbots for a second. So they haven't done too well. I think they started off, there's a lot of hype, there's a lot of excitement. We're like, oh my gosh, all these platforms, messaging, everyone's on messaging platforms. We're going to do natural language understanding. We're going to use the latest deep learning, sequence-to-sequence models, and we're going to have this amazing, amazing time. Everyone's going to be just super excited. And it didn't really work out that way because it turns out that natural language understanding is actually a really hard problem. And I like this example in particular because it highlights that one of the big challenges that we have with doing sort of conversational understanding is this challenge around ambiguity and about context. So here we see that the agent is sort of failing the joke around what the word "it" actually means and what is it referring to. Again, around ambiguity, that's sort of a temporal context issue. We also have this fun sentence, which is another sense of context and ambiguity. So here we only have 10 words. There's 10 words in all, 8 unique ones. And the words flies and like mean very different things, depending on the context of the words that are around them. So how do we deal with this? Like if you just pick it, like again, if you just take some system, you say, okay, I see the word flies. Is it a verb? Is it a noun? Is it part of a noun phrase? What is it doing? And so these are real challenges, and some methods, especially in the deep learning areas, they can kind of sort of solve some of this, but it's really, really difficult. Right. So we're like, hey, we've got these cool methods. We know that your field just hasn't learned them yet, right? We're going to come in, it's going to be amazing, and again, hard problems. So this is what we're trying to do. But the thing that's important here to remember is that while it is hard, it doesn't mean it isn't interesting, and it doesn't mean that there isn't value that we can achieve through the methods that we have right now. So for instance, it's important to talk about what you can do with chatbots. What are the affordances of chatbots? What is it that makes them useful? And so in my opinion, it's around this idea of question and answering. So it's this idea that you can ask open-ended questions. You can ask these phrases, and you can get an answer back. And that answer may be visual, it may be something that's other than text, but that interface is where you can really phrase what you want to say, and you can do it easily, and you're not constrained by some sort of business intelligence tool that has a bunch of structure in place around what you can query, how you can query it. Maybe you have to navigate through multiple pages of something to get to where you want to go. You just want to say what you want. How do I log into my VPN system? Or, what was our revenue last quarter? Or whatever. Simple things, but you want to be able to just say it and get the answer back. You don't want to have to go through a lot of effort. So a lot of the work that's been done recently in this area has been on the NLP side. I think there's been a lot of focus on NLP, especially in sort of the AI and the deep learning communities in the last couple of years. And even around this idea of QA, so like in Facebook a couple years ago did their memory networks, and they could actually train this sort of complicated deep neural network model to on a sequence of simple statements, this Babby data set, and then they could ask questions about it like, Susan was in the kitchen, Susan walked to the front door, where is Susan? And it would say front door. So you could do things like that, but it was entirely sort of end-to-end natural language-based system. And I feel like that what was missing, or what has been missing is getting a lot more popular now, is this idea that Q&A also has a lot to do with the field of information retrieval, or IR. And so most people, you're familiar with IR in the sense of this is Google search, for instance, or Bing. You're just going, you want to get some response back from a corpus of data. And so Q&A sort of sits in the middle of that, where you have your natural language understanding, what is it that the person is trying to get at, and then how do I get the answer out of some sort of data source that I have and get that to them. And so this field of neural information retrieval is sort of coined or starting to show up, sort of appeared for the first time last year at the Neural Information Retrieval workshop at SIG-IR. And then they looked at it again, the second one's happening this year, and we see that the field of IR is sort of getting the same treatment that the field of NLP and computer vision has been receiving from sort of neural methods and deep learning, where it's just sort of taking off. People are trying to figure out how can we apply these methods to this field. And so I'm going to give you a little bit of overview of kind of the key tenets of what people tend to do or what they're looking at from an IR standpoint. So this is your standard information retrieval-based system. And we can think of this as in Q&A as well, that you have some query or a question that comes in, and you have some repository of documents or answers or what have you. And so you have to represent those queries, if they're in text or if they're images or what have you. You have to do some representation. You convert them down to your represented form, and then you do some sort of relevance ranking on those to say, how good is my document to this question? And so, for instance, you might use some basic term frequency based metrics. How many times did this word appear in my query versus how many times did this word appear in the corpus as a whole? And that gives me some hint as to what to do this. So in Neural IR, we can focus on a couple different parts. So first, we can look at the representation part, and this is where a lot of it gets used, and this is things like word embeddings. And so Mukund earlier talked about word embeddings in a kind of a model like this, and we can show you an example of this. So this is work that was done by researchers at Microsoft last year, and they focused on this idea of how to train the word embeddings. And one thing that was sort of that they observed that was sort of fascinating is that a lot of the methods out there, like word2vec or glove or these other word embedding strategies, they take the input features, say the word and the words surrounding it, and they compress down into this dense hidden layer, this dense embedding, and then as part of that training, they might map back out. But so you have this sort of autoencoder style model, you encode and then you decode, but you usually throw away the decoding part. We just use the encoding part, so we get a new term we match down. But they actually looked at the second side of this, the other side of this, and they found that actually gives you different style of embeddings. So the input embeddings actually give you more of a topical representation. Typical representation. So Seattle and Boston are similar in that embedding space. But if you're asking for, like, I want to go to lunch in Seattle, I don't want to get recommendations for places to go to lunch in Boston. That's not very helpful. And so they found that on the outside, you're actually getting more topical representations. So your embeddings are not matching things that are similar in the sense of two things that are the same type of object, but things that are about the same type of object. So that would relate something like Seattle to Pike Place Market or the Gasworks Park or something like that. And so that is much maybe more relevant for the kind of task you might be trying to do. So understanding where your embeddings come from and the kind of similarity that they're learning is very important. So another thing you could do is you could focus on this. You could use this idea of learning to rank. How do I actually create a representation for this? Once I have my representation, how do I learn to do a better job of re-ranking those results, or presenting those results in an effective way? And so there's a lot of work done here. So here's another example. In this case, they're using sort of more classically derived features in this here from the documents. So these are sparse textual features. And then they train a model that actually creates a new sort of semantic embedding, but at the ranking stage. And they're using associated documents here based off click-through. So this is from, I think this might also be from Microsoft. But you're also dealing with this idea that I'm training and trying to relate a query to the documents that were selected as a result of that query and the documents that were presented during a search step. So you can learn to try to figure out what is the right way to rank these by associating this historical information, what is the query and what documents were clicked on when that query or query like that was received. And finally, as is very popular in some of the deep learning areas, we just do end-to-end. We just say, I just want to give you inputs, and I know the behavior on the output, and you figure out the rest. And so we could do both. And so we actually use both representation generation and ranking all in sort of one big model. So here's a work also recently. So in this case, what they do is they use a convolutional neural model to take the sentence representation. They're actually using, in addition to this, they're also using an embedding layer. So they already have a trained embedding layer. They then represent a sentence as a matrix of words and then the embeddings. And then use a convolutional network on that matrix as opposed to collapsing it down in an aggregate way, which is what a lot of other sort of sentence type embedding systems use. Extract features, learn a relevance matrix transformation as part of this, and then they can include additional features, and then they have this sort of, again, final sort of multi-layer process to then get out the probability of how to rank. Cool. So here's a number of resources. This, again, very sort of high level, just to give you a sense of like some of the stuff that people are doing in this. These two references at the top are from researchers at Microsoft who've been doing a lot of work on this. They're both very, very good documents if you want a nice detailed description, especially of ad hoc-based IR retrieval methods. This group, Zhang et al., did a really nice sort of literature review of the current state of neural information retrieval methods at the end of last year. And this includes other areas besides ad hoc retrieval, so like search. So they looked at more Q&A things and other sorts of tasks like query expansion and things you can do. And then finally, there's the Neural IR workshop. Cool. So now I'm going to give you some insights into what we learned trying to implement in practice this conversational knowledge-based concept in our product and using sort of Neural IR. So just to give you a big broad overview, our current approach is that first approach, which I think is probably one of the more common ones in practice right now, which is we use word embeddings, but we're using more sort of standard linear models for the learning to rank part. And I kind of talk a bit about why that is. So first thing, what are we trying to do with this product? And so the goal here, because we need to make sure that the answer gets to the employee. You can't have a system that is trying to respond and just fails and there's no recourse for the employee or the user trying to get an answer, because they need to get that answer. So it's not necessarily the intent is not to automatically answer, it's to efficiently get that answer that they require. And so that could be that one, if we know the answer, if the system can detect that answer, serves that answer up directly. If there is some ambiguity, our approach thus far has been to treat this kind of like as a recommender system, kind of like as a search. And so we actually suggest up to 4 similar types of questions that we know about to see maybe you're asking about this, maybe you're asking about that, and you can choose. And if none of those are right, or if one of the answers that you received just wasn't helpful, there's always a way for you to get to an actual person through your normal service desk process. And the thing is that we're also capturing that interaction. So it's possible to learn and to train the model as that happens. And so one of the things you can do now is that, let's say a question comes in, Talla doesn't know the answer, goes to a rep, the rep answers the question, and in doing so enters it into the knowledge base. So then the next time a question like this occurs, Talla can respond with that answer, or at least suggest it. And then as these come through, this can be built up over time. So over time, you're sort of automating away a lot of your sort of common, tedious, repetitive questions, and now you're focusing mostly on the ones that are more difficult, require a lot more interaction. They're actually getting through to your service reps. So what did we learn? Word vectors. So again, these things are pretty cool. They're really powerful, but they have some problems. One of them is this idea of out of vocabulary. So you've trained your model, you've got your word and vectors, but what happens if a term comes in that is never seen before? So you have no embedding value for this term. And so there's a number of reasons this could happen. It just wasn't seen in your training corpus, or it was too infrequent, it was too rare, and so the model couldn't generate enough information to provide a sufficiently useful embedding. And so usually what will happen in this case is that you replace those terms collectively with some unknown token, and you just replace them. The problem is that in a lot of questions answering or retrieval, individual terms can be highly discriminative, especially if they're rare. So if you only have one instance of this term appearing in your knowledge base and someone uses that, there's a pretty good chance that that might be a good match. And so you make sure you don't miss out on that. And so here's a sort of simple example of what can happen here. We have these two terms, cromulent and bigly, not seen by our model. We don't know what these are. And so we have these two sentences. We can see that if we transform them using this model, a word vector-based system by itself are going to turn it into this. And now these are identical sentences as far as the model is concerned. if you use this. So what happens then? You can't use context here because they're exactly the same. So I can't infer that token from around this in that case. And so what do we do? And so in our case, the solution is to actually ensemble. And we see this a lot actually in the literature for these kind of methods, that the word vectors give you a little bit of a boost, and they can help with some of that fuzzy matching and that semantic matching. But when you're looking at an IR style task, IR methods, they work pretty well. There's decades of research around these things. And so we can see here, and this is the result from the sort of DSM work that I showed earlier, the input and output embeddings. They found that if you use your standard term frequency-based features, the BM25 here, and you combine them with the embeddings, you actually can do a little bit better. But if you just use the embeddings by themselves, you actually do quite poorly. And so this is sort of the key thing, is that we want to make sure that we ensemble with other methods. So you get the benefit of both worlds. So in this case, you can use probabilistic methods or term frequency type methods, TF-IDF, or similar, and you combine them with your word vector features. And that way, rare terms still are very discriminative, still valuable, but if you have some sort of similarity issues or people are using slightly different terms, this is a better approach than trying to guess at synonyms, for instance. We've heard a lot about this, and so I'm not going to go into it too much, but just the basic challenge that operationalizing deep learning can be challenging for a number of reasons. If you don't have enough labeled data, if you can't interpret what's going on, and so you're trying to figure out hey, I rolled out a model, and now we have this weird use case happening. How do I fix it? How do I debug that? Sometimes the performance gains aren't really that exciting. Sometimes they can be tremendous in certain fields, but other times it might be, again, we saw a little bit of a bump, which is great if you're trying to get an academic paper out, but it may have a lot less impact if you're not looking at a lot of high volume sort of interaction. And then how do you do persistence with modeling and all this good stuff? And so to some extent, one of our approaches is to sort of say, we look at deep learning as something that we explore a lot of, and we are evaluating these methods, but for the most part, things are more like offline embedding-based things that we can do sort of carefully and deliberately. But for a lot of online things, to make things fast, to make them retrainable very quickly, we're using sort of just standard linear models. And yeah, if you haven't seen this one, this came out on Wednesday, I think it was. It's a pretty accurate example of a lot of production ML systems. Yeah, so another thing that we learned is that our product is designed to allow the user to train it and to define what goes in it and how that works. So they have ad hoc ability to update the knowledge base, and it has to respond to that. So there's this expectation that if I entered a new piece of information into my knowledge base, and then I immediately ask, do you know the answer to that question I just told you? You should know it. You can't sort of say, oh, well, I gave you that example, and now come back in a day after the batch process is run, and I'll answer your question. That's not an acceptable use case for this product. And so there's this real-time sort of one-shot learning, if you will, style expectation from a product standpoint. So we have to be able to support this. And again, also the fact that the user themselves is defining through this interaction how the data comes in. And as we know, with user-driven training models, bad things can happen. So if you don't recall this, another Microsoft reference, this is Tay. Tay was exposed to Twitter for about a day and became somewhat unpleasant. And so, this was, again, we want to make sure that we allow for these sorts of things to not happen, or if they do, that they can correct it. So it's really important that you understand as an end user what is in the model, and if something is a mistake that happens or something goes in that you don't want, you need to be able to see that and you need to be able to correct it. So we expose the entire knowledge base of what has been learned via a web interface, so you can see it, and then we use this sort of cascade model for online and sort of nearline learning. So very short, sort of quick way to do a good approximation that as soon as you've trained or added a new element, the model will understand that and respond, and then sort of based on the fact that, again, we're using sort of lightweight linear models, we can retrain these things almost, not in real time, but very close. And so, while we're waiting, you can retrain sort of in a queue, background process, get that information in quickly. And again, it's just really easy to understand these models and to use, say, term frequency-based models when you're trying to understand why certain things are happening. and why certain things are being surfaced. Finally, this one was interesting, and has nothing to do with machine learning. It's that it turns out that conversational interfaces, sometimes users don't actually read what the agent is saying to them specifically. And so here's an example. I'll say what'll happen is that you tend to skim. You sort of like, I have a mental model, again, of what I think you're supposed to say. I see some words. I don't actually read them one at a time carefully. I kind of skim. I see some words. I make an assumption about what the response is, and I respond immediately without really carefully looking at it. And so in this case, we see this is from an experiment we ran several months ago of building sort of a purely conversational, natural language-driven task assistant. Remind me to do things, add this to my task list. And here's a case where a user asked to do something. The sentence they used, if you can see it, maybe it's a little small, is actually kind of hard to parse even just reading it. Add take dog for a walk to list for next week. And so the agent, the parsing model did not do a great job of this. It messed up. And what's happening here is that then the agent is asking, is this correct? Should I add this to your list? Yes or no? The agent is now in a conversational dialogue state where it's expecting a yes or no response. The user did not see that part. They just saw that it was wrong, and they immediately tried to correct it by saying the line again. The agent, of course, is waiting for a yes or no response. Didn't like that because that was not a yes or no, and responded again with an error message. And again, the user is still trying to do different things. Finally, we sort of had a fallback to say if we had several interactions that were poor, to sort of really emphasize the fact that we were asking for a yes or no answer, and then finally they got it. But this is a problem. You have to be very careful with these sort of pure conversational interfaces because people just don't actually read right away. They skim. They make quick decisions, but they may not read. And so if you're asking and you go into some sort of expected dialogue tree or state, they may just jump right out of that, and then how do you recover from that? It can be very challenging. So the key, right, is to use, one, we just sort of constrain. Okay, let's lower, to some extent, let's do expectation management. What can the bot actually do? What do we want? And let's really emphasize the hybrid nature of the interface. So again, these are examples from Slack. And so here, what we have is the question was asked. We give a response. We show you as much as we can using sort of all the decorations and UI elements that we can within the interface. Plus, we now use buttons, right? Other sorts of little visual widgets, because those are much clearer to see. They're more salient to the user. And so you give a response. Do you want a yes or no? Do you want buttons? So things like buttons, widgets, those are actually a better representation to help the user be successful. Same way as if we don't know the answer, or if we don't have a high confidence, we need to make sure, again, like I said, that the user can get to a person. And so we give them that insight, but then we allow them to go ahead and open the ticket. So in summary, conversational interface and QA in general is not, it's not just about the algorithm side. There's the user behavior side, and there's a lot of things you have to take into consideration when you want to actually deploy these in practice. No amount of like hand tuning your special classifier algorithm is going to maybe deal with behavioral change issues. Neural IR is a very exciting and fast-growing field, especially, and I think it was sort of underlooked for people trying to go into sort of this Q&A sort of model, unless they were familiar with that area. And then finally, chatbots can actually be useful, but they need to be very like constrained in the expectation of what they can be good for needs to be set. Thank you. Just think we have time for a question or two. Yes.
I'm going to take it back there.
So the question is, how do we represent context in those conversations? So in that sense, we're actually doing a fairly limited amount of interaction right now. And so everything is very, very constrained to sort of short messages. There's a lot of context that is implicit in the interaction that we're capturing. But in terms of context, like I kind of talked about at the beginning, around, say, anaphora, co-reference resolution, things like that, we're actually we're not doing much with that at the moment, just because, again, we're trying to focus more on the experience. So we're limiting the expectation of what can be done there. As we're collecting this data, we're analyzing and working on it, but at the moment, we don't have a clear solution. Yes?
For your founder there? Yeah. So I help run mini analytics in Minnesota, here from
so the question is, how do we deal with sort of the updating of the model sort of in reaction to those inputs?
Business card and I got it from someone up front.
So at some level, so this product is sort of, one, is segmented by organization. So there's actually a model trained per organization on their unique knowledge base to provide. And so depending on how dense or sparse their knowledge base is can affect, again, the size of the model and how quickly it can train. But there's a scaling problem there. Because as it expands, as it fills up, these methods will slow down. And so to some extent, what we do is, it's at a level right now where it can actually train, again, the models are very, very fast to train still. And people aren't really asking questions like in microseconds. They might ask them every so often. And so because of that, we do have a bit of leeway there. The case I kind of mentioned of the sort of cascade is largely in the case of people who are trying to understand, like, is it really working? And so they might store something and then immediately try to ask another question. And so there we have sort of a very simplistic working memory type of system, if you will, where it's sort of attached to the model as sort of an additional layer where it comes in and it checks to see if anything has been added that hasn't been synchronized yet, and it looks at that first in addition to the model. And so there's sort of this ongoing caching process that we do. Yes?
So in that conversation approach, there's actually the next cycle of the concept, how long the concept is, right? Do we need to kind of factor the human concept? Because some people see work having one concept with another, some people are so
So is the question sort of how to deal with how different people's behaviors and how they, yeah, so I guess the question is, given that people respond differently, interact differently, some people might be very context heavy in their communication, they might be very specific in their communication. To some degree, with these models, what you can do, and sort of what we found is that to ensure that it works better, as long as it's solving a problem that people are willing to invest the time, you can actually just but you constrain the problem to encourage them to be specific. So in that example with the task assistant, we did have a model that allowed you, it's like a CRF-based model to try to tag out the task part and the time part without any sort of additional information. But what we encouraged people to do, especially if it didn't get it right, was to use quotation marks. To like sort of help us understand what they want. And so you can kind of, again, look at this also as somewhat of a behavioral issue where you can nudge people to do the thing that makes them succeed faster than trying to solve these sort of arbitrary problems. Cool. I think that's it. Thanks again.